a better thing to do. Don't mess with the rules. Just do what you can do. Everything is unstable, so you think this is not going to work. But this idea that I have a compact rubber band says, well, it has to work because rubber band has some value and that's it. You can't do anything about it. So find a solution which is every place unstable, but obeys the law every place. So if I deviate, I run off the road, but because I'm this rubber band, I will never, cannot run off the road because I know where I'm coming from and where I'm going to. So I'm guaranteed to be there. I just have to make sure that I'm obeying the rules of the game. It's compactness that enables you to solve these unstable problems. Now, you might think it's much easier to solve stable problems than unstable. But it turns out it's actually much easier to work with unstable problems. So with unstable problems, what's happening is you see it in the unstable manifold. If I throw a knife at the unstable manifold, I cannot hit it because it's a line, it's infinitely thin. But if I go to the left of it, I glance and I'm thrown to the left side much further. If I go to right of it, I'm thrown to the right. So this edge, this unstable direction is very easy to identify because I either am bouncing left or right, and the correct answer is in between those things. So finding unstable quantities is much easier than finding stable quantities. Just keep trying to get to them until I pin them down. And every time I make an error, I get thrown away. And that's, the idea of all these calculations. I try to find something that's just on the edge of being unstable to the left and right. That's called Lagrange-Euler equation. That's what it is. Lagrange-Euler equation says, I'm right there where they're balanced. If I go to the left, I fall off this side. If I go to the right, I fall the other side. And that's the meaning of demanding that the first derivative of my potential is zero. Then I'm on plateau. I'm not being pushed anyplace. So it's built in this formulation. And there's nothing wrong with being unstable. It's perfectly fine. And it's actually, if you think about it, it's easier to compute than stable things. When you have a Hamiltonian system, you're trying to find a stable fixed point. It's a point that has little circles, ellipses running around it. So when you take a guess, you just find yourself oscillating around that you somehow have to improve your guess so your radius of oscillation is smaller. But it's a harder problem than finding hyperbolic point. This hyperbolic point, either I go this way or I go that way. Let me try to stay in the middle. So those guys, nicer, easier to deal with. So it's counterintuitive, but it's just counterintuitive because of our education. It's not because, it's totally sensible when somebody explains it to you.